This set of notes is about cell potential, free energy, and the equilibrium constant. Set of notes has been provided for you. You know the drill. All right, so in our previous set of notes, we talked about how a battery cell or a voltaic cell is set up. So how do we measure the level of electrons that are transferring through a voltaic cell? Well, we use that. We measure that transfer using electromotive force, or EMF. If you think about a waterfall is only going to move from high to low, right? It starts up high, it goes down low. In terms of gravitational potential energy, it has a lot of gravitational potential energy up here at the top, much less at the bottom, and therefore it is always flowing toward a place of lower potential energy. Same thing happens in a battery, okay? In a redox reaction, electrons only flow spontaneously in one direction. They go from higher energy to lower energy. So that's how we end up with an anode and a cathode. They're always going to flow from the anode to the cathode. Why? Because the cathode is a place of lower energy and the anode is a place of higher energy. The potential difference between the anode and the cathode is called the electromotive force, or the EMF. Okay. In chemistry terms, we also refer to this as the cell potential, and we designate it as E cell. We measure it in the electrical unit of volts, and a volt is just simply a joule of energy per coulomb of charge. All right, so if we want to know how much work a particular battery is capable of doing because the electrons are being transferred through it, we can go ahead and we can use what are called standard cell potentials, or sometimes they're called standard reduction potentials. Okay. They're standard, so again, standard means we're talking about the chemicals being at standard conditions. So if it's a gas, 1 atmosphere of pressure. If it's a solution, 1 molar concentration, and of course at a temperature of 298 K. Okay, so if we want to figure out the cell potential, or how many volts a battery is able to produce, what we do is we take the reduction potential of the cathode minus the reduction potential of the anode. Okay, so E reduction is the standard potential for the half reaction happening at each electrode. Okay, it's based on reduction, so it can be either negative or positive. Okay? If it's a reaction that's mostly oxidizing, then it's going to be a negative reduction potential. If it's based on reduction, it's going to be positive. Okay? And it's based on reference to something called the standard hydrogen electrode, which we'll talk about more in a second. Okay? So if you think about it, reduction is just the opposite of oxidation. So if we want to find the standard oxidation potential of something, we just reverse the reduction equation and change the sign on the reduction potential. Okay, so that actually makes it easier for us at the end for us to go ahead and just add the reduction potential and the oxidation potential, because all we need to do is figure out then what's being reduced and what's being oxidized, and make the signs correct and then add those things together. People oftentimes have problems with this first one because they forget which order do I subtract them in, what's the cathode, what's the anode. So a lot easier we find if you go ahead and you just figure out what's the reduction, find the reduction potential. What's the oxidation, find the reduction potential of that, flip the sign, add them together. All right, so let's talk a little bit more about the standard hydrogen electrode, also called the SHE. Okay, standard hydrogen electrode by definition has a reduction potential of 0 volts. It's sort of the reference. So any kind of reduction potential is referenced to that standard hydrogen electrode. And basically it is the reduction potential of hydrogen ions turning into hydrogen gas. Okay, that process is given the reference of 0 volts. Okay, so because they can be referenced to the SHE, many reduction potentials for different electrodes have been measured, and we find them in a table like the standard reduction potential table. Okay, so there's a whole list of them right there, and we can go ahead and take a look at them and then use them in the manner that we described before mathematically to figure out how many volts a battery is going to produce. All right, so if we go back to this battery that we've talked about before that has zinc electrode, and it has zinc solution, and it has a copper electrode and a copper solution. And in this case, we can tell from the picture, if we don't remember from our previous discussion, what's being oxidized and what's being reduced, right? So oxidation is losing electrons. So I'm going to look at my two solutions and I'm going to see where are electrons being lost by something. Well, they're being lost right here by this solid zinc, right? 2 electrons, and they travel through our wire. So zinc is being oxidized. What's gaining electrons? Well, we can see it right here. Copper ions are adding to electrons and forming solid copper. So that's our reduction. Okay, so if I go and look at my standard table, I'll see that the standard reduction potential of zinc is negative 0.76 volts. Okay, because we know that that's what's being oxidized, we just flip the sign on it, 0.76 volts. Okay. Oxidation happens at the anode, so we do know that this is the anode side. Anox, right? Copper, we decided was being reduced from the picture, all right? And so if we go and we look at copper's oxidation potential, or excuse me, reduction potential, we see that it's 0.34. And since this is the reduction, we just leave the sign as it is. And reduction happens at the cathode, a red cat, right? Red cat and ox. All right, so if we go ahead and take a look at that, then we now have E-ox and E-red, so we can figure out the overall potential of this entire cell by taking those two things and adding them together, which is exactly what we did here. So 0.34 volts was the reduction potential for copper. 0.76 volts is the oxidation potential for zinc. We add them together, and we get plus 1.10 volts. Okay. One final note about calculating E-cell. This is huge and an error that people always make. The number of moles does not matter. So if in a balanced equation, or what we see going on here, we get a situation where we're getting 2 electrons transferred on one side and 1 electron transferred on the other side, it doesn't matter. You do not have to double, triple an equation. Do not multiply the standard reduction potential. It is constant for a particular metal or reaction at a particular state. So just got to figure out what's oxidation, what's reduction, flip the sign for the reduction potential on the oxidation, add them together, don't multiply anything. All right. So in our previous example, we figured out what was being oxidized and what was being reduced by looking at the picture and seeing what the picture was diagrammed. But of course, in real life, we don't typically have that. So how do we know what's going to be oxidized and what's going to be reduced? Well, basically what we can do with this is we can know this a couple different ways. One, if we have an activity series, as we talked about earlier, this unit, whatever is more active or higher up on the activity series, that gets oxidized. Whatever is lower on the activity series is reduced. Okay? In electrochemistry, we can also figure this out from the reduction potentials. The more positive reduction potential is reduced. The less positive is oxidized. Okay? So the more positive reduction potential. So more positive could mean less negative too, depending upon what's going on. But the more positive reduction potential is reduced, the less positive reduction is oxidized. Okay? More positive happens at the cathode, less positive happens at the anode. So as an example of this, if I just looked on my chart over here and I had a battery that had silver ions in solution and it had copper ions in solution, we would know, oh, this is more positive, so this is going to be the reduction. This is less positive, so it's going to be the oxidation. Okay. Likewise, I could do some other ones on the other side, right? Negative 1.66, maybe we have aluminum, and maybe we have fluorine ions, okay? More positive, going to be reduced. Less positive, going to be oxidized. Okay. If we come back to our terms of oxidizing and reducing agents, which again is not a term that they'll ever use on an AP test, but is a common term, the strongest oxidizers, okay, so again, that's where reduction happens, have the most positive reduction potentials. The strongest reducers, so again, that's where oxidation happens, have the most negative reduction potentials. Okay, and so they go in opposite order of each other. Okay. The greater the difference between the two, the greater the cell voltage. All right, so in our example earlier, we saw that copper had a more positive reduction potential, so it was what was getting reduced. Zinc had a negative 0.76, so it was what was getting oxidized. And the difference between them is the voltage. Well, you can imagine that if one is reduction potential is even more positive and the other one is even more negative, then you're going to have a greater voltage in your cell. All right, so then the last piece of this that we need to talk about is we said earlier that cell potential is related to work that can be done by a cell. Well, we learned in our last unit when we were talking about free energy that free energy is also a measure of work that can be done by a cell. So that means that there's got to be some relationship between cell potential and free energy. And there is, okay? That relationship is given to us by the equation delta G equals negative NFE, where N is the number of moles of electrons transferred in a redox reaction. So for example, if we were doing a balanced equation and we saw that there were 2 electrons being transferred overall or 6 electrons being transferred overall in our balanced equation, that is the number of moles. 2 or 6 would be what we put in for N. Okay. F is the Faraday constant. Okay. F is the Faraday constant, which is 96,485 coulombs per mole, or 96,485 joules per volt mole. Okay. Note again that this is done in joules as we sit there. And of course, E is the cell potential. Okay. Under standard conditions, we can then go ahead and figure this out. We can use the standard form of that equation. So delta G standard equals negative NF E cell standard. All right. And if we then combine that with RT ln K from our previous unit, that would allow us to find the equilibrium constant. So not only can we relate cell potential to delta G, the free energy, we can also relate cell potential to the equilibrium constant. Okay? These equations allow us to determine the spontaneity of redox equations, because if delta G is negative, we know that the redox reaction is spontaneous. If delta G is positive, we know that it is not spontaneous. Okay, in other words, we'd have to put electricity into it in order to make it work. All right, so we then use that equation. We can figure out whether delta G is negative or positive using our cell potential, Faraday, and our equation. All right, those are the basics that you know. Some equation manipulation that's going to need to happen here with cell potential and free energy, but other than that, that's what you need to know about cell potential, free energy, and the equilibrium constant. Have a great day.